Yeah, and to discuss a couple of technical details of the word-to-vec model. So how does it basically work? Like as so this is our so there are two different architectures. One is called SIBO skipgram, and jointly together they are called word-to-vec. And what these two architectures do is basically, given some word and some text, they want to predict the surrounding words. So, or the alternative is, given the surrounding words, they want to predict the word in the middle. So this is the task they want to solve, and the way that they do this is they start out with discrete representations of words. For example, the cat could be the second word in the alphabet, love could be the fourth word in the alphabet. And then so this is also a neural network. In this neural network, they learn a so-called embedding matrix E. So this embedding matrix is here. They learn this, they train their neural network. And as you see, a one-hot vector comes in, and if this one-hot vector is multiplied by this embedding matrix, then we get out exactly the corresponding vector at the index that corresponds to this word. So we would get this vector, so the fourth index, so we would get the fourth row of this matrix, and this fourth row is exactly is then the vector representation of the fourth word in the vocabulary. So yeah, that's what these models are doing. They are training, they are trying to solve a specific task, namely from given a word as input, predict the surrounding words, or giving the surrounding words as input, predict the middle words. And once they have solved this task, the task is not important anymore, but what is important is the vector representation. And why this model is a good idea to model it exactly in this way, we will learn in lectures 4 to 6. But here you should just get the high-level basic idea that we, as a byproduct of solving this model, we get a vector representation for each word. And what has been shown empirically is that these vector representations are good in the following sense. Namely, we have observation number 1. Semantically similar words, so words that are intuitively considered to capture the same meaning, they are near this vector space. And observation number 2 is also that syntax and morphology, or their properties, are somehow also encoded in the vector space. But we'll focus on semantics now. For example, that could be a representation of the vector space in a two-dimensional projection. So usually these vector spaces are at least 300 dimensional, but for visualization purposes we now plot them in a two-dimensional space, because humans cannot go beyond r to the 3. So, and what we would typically see is that you see obviously words that have similar meaning, for example battery and charger, or paint and color, or oven and refrigerator. So intuitively you would say that these words have similar semantics, they have a similar meaning, and we find that indeed these words end up close being in this vector space. And the cool thing is we can even do this across 2 languages, or across 3 languages, or across 300 languages. And what we then see is not only that words within one language are close to each other, words that are intuitively having a similar meaning are close to each other in one language, but also across languages. For example, we would see here Vater and man are close, Id and Essen are close, and Gabel and Essen is close, and trinken and drink is also close. Yeah. So you can generalize this across languages, which is a really cool thing, because then you can go beyond the specifics of a particular language and just do global natural language processing across all possible human languages, ideally. And the most fancy current techniques in this context are so-called contextualized embeddings. So in the previous approaches, and these contextualized embeddings, they came about in around 2018 with a model called Elmo. And here you see these people from the Muppet Show, Elmo and Bert, or maybe this is Elmo, I guess, and this is Bert. What these models differentiates them from the previous models, such as Word2Vec, is that now, depending on the context, each word gets a different embedding. So the previous approach had that each word has exactly one embedding, and this results to obvious problems in case of a word having multiple senses and multiple meanings. For example, the word can is given here in two sentences, and you see that it's used very differently. In one case it's a verb, in the other case it's a noun, and it has very different meaning. But the old models like Word2Vec, they would give the same vector to these models. But now these contextualized embeddings, they give embeddings based on the context. And they have become super popular after 2018 with Elmo first. And then quickly after Elmo came Bert. And Bert is even much better than Elmo. So, but I think nobody's using Elmo anymore. So Elmo was very short-lived, just like half a year or at most 1 year. After that, right away, everybody used Bert because it was super powerful, and it also changed a little bit the way that natural language processing is done. And we will hear more about that in lecture 5, I guess. Okay, so this was the input representation. So we have these embeddings, they capture semantics, they can be static or contextualized. About architecture, so we have one architecture that is very popular in image processing, and this is called convolutional neural network. This has a so-called translation invariance. So translation has nothing to do with machine translation here, but like with the property of location of an object. So an object could be located differently across an image, for example, but still the image should be classified the same. So no matter where you see these eyes and ears here and the nose, you would say this is a cat. So it has so a model is good if it can give the same classification no matter where the object appears in the picture. And convolutional neural networks, they have a built-in translation invariance because they do so-called parameter sharing. So in standard neural networks, all the weights can be adjusted, they can be adapted, so you can learn to change them independently of each other. But in a convolutional neural network, you have weight sharing. So some weights always stay the same. So they are jointly. So if one changes, the other also changes. And this reduces the number of parameters and leads to this translation invariance also. So more to the natural language processing side, what we have been using, well, let's say at least until 2018, 2018 were so-called recurrent neural networks, because in natural language processing we often have sequential data, so temporal data, so to speak, because words appear in a sequence, so you naturally have a sequence. And often we want to classify each element in the sequence, right? So we have temporal data or sequential data. We want to do a classification at each time step, so to speak. And the classification usually depends on the history. So whatever what you have seen earlier influences your decision, how you would label some current unit at the current time step. And the RNNs are the standard workhorses for such data. And because we have many such tasks, we have like part of speech tagging is a classical task in NLP that requires to label each element in a sequence, also named entity recognition, where you have to say whether this current word under scrutiny is a person, or is a person, or is a what else could it be? Is it an industry, or is it nothing of those things at all? So this is named entity recognition, and this is also a classical sequence tagging problem for which RNNs can be used. So how do they look like? So what we've seen before here is we have seen a standard neural network. We have like a multi-layer perceptron where we have input, we have one hidden layer, and then we have an output layer. And yeah, and then in this output layer we do some classification, we give a label. And recurrent neural networks, as the name already suggests, they have a recurrent connection. So the hidden state feeds back upon itself. What does that mean? So it means it is informed by the previous hidden state, and you can unroll such a neural network in time. So this is the equivalent representation, that's called unrolling. So at each time step you have an input, I can see. You have the hidden states at each time step, and you see that these hidden states are informed by the previous hidden states. And because they are informed by the previous hidden state, if you are up here, you get information from this hidden state, and this hidden state is informed by this word. So when you are here, you do not only have your current word as input, but you are also informed via this indirect direction about information that is one time step past. And of course you can go back. And because this hidden state is also informed about its previous hidden state, you're also informed about two time steps past, what has been input 2 time steps past. And of course you can go back infinitely long, so you really have the whole history at your disposal when you want to make a new classification. So when you want to classify this can here, then you have the whole history at your disposal, and you know that the context here is I. And if a pronoun, or like if something like I precedes the word can, then it's much more likely that this is not a noun, but that it is actually a verb, and in particular an auxiliary verb. Good, then finally the third architecture is an encoder-decoder model. As I've said, they're ideal for mapping an input sequence to an output sequence, which can be of different length, and the order of the elements can vary. That's in machine translation between languages that are not closely related. And encoder-decoder models, like also up until 2018, they consisted of 2 RNNs. How do these architecture look like? So we have one RNN here, and we have another RNN here. So these are like slightly modified RNNs. So the first RNN does not have an output. The second RNN does, so to speak, not have an input. What the first RNN is doing, it is representing the input in the hidden state. So like it takes the input, and then it represents all of what it has seen in this final hidden state, and then it's feeding this final hidden state in the initial hidden state of the second RNN, and this second RNN starts to generate output tokens based on this hidden representation. So it starts to generate the first one, then the second one, the third one, and it generates as long as it has not encountered an end of text symbol. And we could translate a German sentence into an English sentence with such a model, like sie mag Katzen gerne, into she likes cats. Now, beyond these classical architectures, we have seen a couple of interesting extensions in recent years. For example, we have seen multitask learning in the context of deep learning that has also been popularized very much in natural language processing. In multitask learning, instead of learning only one task, at one point in time, you learn multiple tasks at the same time. And this is also very much like humans do. So you might learn several languages at the same time, or you might do several computer science courses at the same time, and you do not do them independently. But actually what you learn in one course is oftentimes very helpful for another course also. And this is the idea of multitask learning, that if you learn tasks jointly at the same time, you get spillover effects such that you're informed by the other tasks, and this makes your model better. So this has been a trend very much under focus until like between 2016 and 2018. Now at the moment people have gone slightly different ways, but I think this is very promising idea and will also probably be influential, very influential in the long term. And another cool thing that has come up in recent years is adversarial networks. There the idea is that you have two networks that compete against each other. So you induce a competition situation where one network is generating something, like it may be generating an image, and then the other neural network has to decide whether this is a real image or whether this is a generated image. Like, is it an image that has been photographing a real human, or is it a made up, a fake human? And you can imagine if you have these two networks competing against each other, it's like two adversaries that compete against each other, like police versus counterfeiters, where counterfeiters are in German Währungsfälscher. So these are people who try to make fake money, and these counterfeiters, they generate fake money, and of course if police is quite bad, so this is the second network, is if that police is quite silly, they can also make money that is also very silly, right? So that is not really convincing. But if police is good, then also the counterfeiters have to be very good. So if police is clever, the counterfeiters are clever, and they try to outsmart each other, try to be better than one another, and over time they reach an equilibrium where the counterfeiters are just producing fake money that is indistinguishable from real money. And so this is the metaphor, and as a result we get a neural network that is really generating output that cannot be differentiated and cannot be distinguished from the real data that it has been trained on. And these networks have seen a huge success in image classification. You see here, this is from one popular paper where they trained on a celebrity data set, and then they generated fake celebrities, so to speak. So they generated these guys here that are not real humans, but they do look very much like real humans. And in language modeling, a similar idea in natural language processing is language modeling, where you want to generate text. So you do not generate an image, but you generate text, and of course you could also use these generative adversarial networks for this. This has not witnessed so much success in NLP, but instead there are different architectures in NLP that are being used. So traditionally we had a recurrent neural network as a model to generate text, but now in recent years different architectures have come up, like the transformer model, that are pre-trained. So this is also a recent innovation, that you pre-train these neural networks on general data. So you find good initial solutions for these neural networks by exposing them to the whole of the web. And if you do so, you can get language models that actually perform, or you can get neural networks to perform quite well. And in the particular situation of language modeling, they can actually produce text that is quite convincing and much better than what we have seen previously. If you want to try that out, then you can go to that web page here, and you type something in like, this course is really, and you try to have the network complete your text, and you find that in this case the result is not very convincing, so you try it out another time and it will generate for you. This course is really interesting for students interested in project-based learning, or if you are just curious about neuroscience and our limbic system. And as you can see, this is a very good summary of what we have been talking about. And so we stop here.